Hey physics students, it's Mr. Thrasher again. This is a video going over the solutions to the wave speed homework. This one's probably going to go significantly faster because a lot of it's just doing math. But I have both the numerical answers and especially for a handful of these, there are some tricky pieces and I want to talk about those pieces as we get to them. Just like before in the last video, feel free to skip ahead to whatever problems you may have missed. And of course, you can email me any questions if you still have some. Okay, let's go ahead and get started. For number one, definitely a math problem. It says that we have a wave on a string. It gives us the amplitude of that wave. And here's maybe the first little tricky part of this assignment. There is no equation that we've learned that has amplitude in it. This 0.1 is actually not needed anywhere in this problem. You should understand, obviously, what values and what things are associated with, like the wave speed equation. And amplitude isn't one of them. It gives us the wavelength. It says that it takes 0.9 seconds for one complete wavelength to pass a given point. It's asking to find the speed of the wave. So here's my equation, v equals f multiplied by lambda. I'm looking for v, pretty straightforward. I know that the wavelength is 0.4, but 0.9 is not the frequency. Frequency, remember, is measured in hertz, or 1 over seconds. Remember, it's like the number of vibrations or the number of waves per second. The number we were given was in seconds. That's a time. And it says in here that it's the time for one complete wavelength to pass a given point. That's the period of the wave that we're given there. So you have to do a little bit of a side adventure. You were told the period is 0.9. You plug that into our pretty easy equation to get frequency. The frequency is 1.11. That's what you plug in right here. I get an answer of about 0.444. It's a speed or it's a velocity. The units are meters per second. That's number one. Number two, you're given two frequencies in this example, and essentially you're asked to do two calculations using the known speed of sound. And remember, it's a constant. So even if there's a problem and it just says, without giving you a number, like a sound wave is traveling, unless you're being asked to actually calculate this speed, you could just plug in 340. That's going to be our easy constant, because that's pretty much the speed of sound at like sea level, normal temperatures, things like that. But we're trying to do two calculations. Find the wavelength when the sound waves have this frequency. This is the lowest note the piano plays. And find the wavelength of the sound at this frequency, at the highest. So I've organized it by two different frequencies. You don't necessarily have to do it like that. But I plugged in my values, 340 for V. I plugged in the two different frequencies, and I got 12.14. That's the biggest wavelength. And 0.081. Wavelength is measured in meters. That's number two. Number three. It says that the speed of all light waves is 3 times 10 to the 8th, and that should be a callback to what we learned about in our past videos. The speed of light is constant, similar to how the speed of sound is essentially constant. Okay, what's maybe a little tricky is that I know when you think of light, you think of reds and greens and blues, but light, this 3 times 10 to the 8th, that corresponds to all those different types of light beyond just the visible light from the video. Radio waves are light. X-rays, UV, infrared light. We're going to be spending more time on that once we get back from break, but all of those things are light. They all travel at the same speed of 3 times 10 to the 8th. So my equation, it is still technically V equals F lambda, but now V is just the speed of light. It's a constant. There's one less variable that you have to worry about. Okay, and now I can plug in that frequency that it gives me, 8.8 times 10 to the 7th. Many of you probably did this right, but if you did not get about 3.4, you're doing something wrong in your calculator. This requires scientific notation. Remember that notation that we did before? It's still important for this unit because we have these big numbers. So that's what I get for number three. Okay, moving right along. Number four, it's asking you to find the wavelength, and this is a good problem because when you read this, all it seems to give you is a frequency. If I know this equation, how could I solve for the wavelength if the only value I'm given is f? Well, I know what the speed is. X-rays are a type of light. Even though it's not directly stated, all light has a speed of 3 times 10 to the 8th. So even though it's a little indirect, I know two of these three terms. Again, I can solve for wavelength. Again, check your ability to put this in your calculator. I get 1 times 10 to the negative 10, still being measured in meters. That's 4. Number 5, a tuning fork. Okay, a tuning fork is producing a sound, and it says that that frequency of sound is 256 hertz. All right, it gives us the wavelength of 1.35. Find the speed. So this time it's actually asking you to calculate the speed. I wouldn't just plug in or write out, oh, it's 340 because Mr. Thrasher said. Okay, it is true that 340 is more or less the constant, but let's just double check. In fact, what I wrote down right here, hopefully we get an answer of around 340. If you plug this into your calculator and you got an answer of 12, well, if you remember what we learned about sound, hopefully that would kind of make you pause and be like, well, wait a minute. Mr. Thrasher said the speed of sound was more or less 340. If you got an answer very different, maybe you'd go back and double check. If you plug in the numbers, I get around 345.6. And that pretty much matches our check. Okay, again, it does depend on like the temperature of the air, the pressure. So different altitudes can have slightly different speeds of sound, but it's not varying dramatically. It's like, 338, 340, 346. It's never going to be as low as like 12. It's never going to be as high as 57,000. It's always around the 340 range. Okay, that's number 5. Number 6. Okay, for number 6, we got to do a little deducing here. It starts off by telling us that a wave is vibrating back and forth 3 times each second. And it gives us the wavelength. Okay, it says the wavelength. So this is pretty obvious. We were just told what that is. We're trying to find the wave speed. So here's our equation. We were told what the wavelength is. We're trying to find v, but what is that frequency? Make sure you understand what this is telling you. Okay, if something is moving 3 times, back and forth 3 times in a second, that's the definition of a frequency. Frequency is how many wavelengths or oscillations or vibrations or back and forths per unit of time or per second. So in a hidden kind of way, slightly I guess, this 3, that's the frequency. So that's what you plug in for f. 3 times 2, that's 6. Next problem. Number 7. Okay, this is a conceptual question. Oh, looks like my diagram got a little messed up. It says the wavelength of a sound wave is reduced by a factor of 2. So we go from wavelength, so some lambda, and it's reduced by 2. So that means it's like 1/2 as much. So I'm cutting it in half. I had a certain amount of wavelength, and now that wavelength is smaller. It's half as big. There's 2 questions. What must happen to the frequency, and what happens to the speed? To be honest, it's a little easier to answer this second question, because if they're not saying anything else about these sound waves, they're not saying you're going to, radically different temperature areas or radically different altitudes. Remember, the speed of sound in this class is pretty much constant. So the speed of sound is staying the same because the speed of sound is pretty much constant. Well, that answers this second question, and that really helps us answer the first question. So I know that the wavelength is going down. It's half as much. Well, I need to have the same speed at the end. So if this is decreasing, and I must have the same thing on the left-hand side of the equation, the frequency must, or I can't draw a straight line apparently, must be going up, right? If I have 6 is equal to, I don't know, let's say 6 multiplied by 1. Okay, the speed, the frequency, the wavelength. And then I say, well, let's make this half as much. Let's make this 3, right? Half as much. Well, if I still have to equal 6, this number, the frequency, has to go up. And how many times does it have to go up? It has to double. So the frequency has to double. Oops, I should probably put that right there. Okay, that's the answer there. Okay, so for 7, the speed stays the same. The frequency would have to double. We're almost done. Number 8, another conceptual question, and I expect that you're going to give me some props in the comments below based on my awesome drawing abilities. It says that different musical instruments play different notes, and especially if you're thinking like of an orchestra, playing some kind of piece of music, you don't have all the different musical instruments playing the same note, middle C. That's not a song. So if we think of at any given time an orchestra, maybe we have like a trumpet and a guitar or a cello and a flute. And, at one point in time, they're playing different musical notes, okay, to make it nice, to make it different sounding. It says in the question, by listening to a band or an orchestra, how can you pretty easily conclude that the speed of sound is the same for all frequencies? Okay, so I have all these different frequencies. How do I know? How can I kind kind of easily prove to myself, I'm not saying do a full math or science lecture or proof, that the sound is traveling at the same speed for all those different frequencies. Well, let me ask, if you've ever been to a concert or an orchestra, or even just listening to music on the speakers when there's more than one musical instrument, do you ever sit there and go like, oh man, all right, there's the flute. Now get ready, here comes the trumpet. Ah. Oh, okay, get ready, the guitar is gonna come up next. Ah. If you see all of them start playing at once, well, they start producing sound in your ears at the same time. So if you're hearing them at the same time, then it must mean that whatever this distance these sound waves are traveling, and maybe my diagram isn't perfect, but roughly all the exact same distance, right? Well, if they're covering the same distance and reaching your ear at the same time, they kind of have to be traveling at the same speed, right? Okay, when two musical instruments play at the same moment and they're playing different musical notes, you still hear both sounds at the same time. So the frequency doesn't affect the time. There, that's a pretty good answer. Last problem, number 9. I'm sorry, that's not the last problem. Second to last problem. We're making some quick sketches. Okay, so this is kind of my base graph, my base wave, and it's really, this question is asking for you to interpret the idea of pitch and the fact that pitch relates to frequency and that loudness relates to amplitude from our video. So for A, a higher pitch, that means a higher frequency, more back and forth, back and forth, back and forth, back and forth. Okay? If it says the same volume, I should have the same amplitude. So I know my drawing abilities aren't great, but whatever this amplitude is, it should be the same amplitude, but higher frequency. For B, louder, bigger amplitude, bigger. All right, but the frequency should stay the same since the pitch is staying the same. Okay, you can read C. For D, oh, sorry, man, my video is a little bit out of the way. If it's a higher volume for D, there should be a higher amplitude. And if it's a lower pitch, it should look like this, really spread out, something like that. Sorry, my webcam's kind of covering it. Okay? Number 10. All right, so for number 10, our last one, it's a good conceptual question. Okay? It says that you hear someone playing trumpet across the room where the air particles that were vibrating near your ear carried across the room by the sound waves. This is kind of a key idea from what we were learning about in one of our videos. Okay, here I have somebody shouting. Maybe this is Mr. Thrasher. All right, you're in the room and Mr. Thrasher starts shouting. Especially nowadays with Corona, you got to be careful, right? You got to wash your hands. You want to have a certain distance away. Should you all of a sudden be concerned because those air particles that were next to my vocal cords are now traveling across the room and into my ears? This should hopefully be a pretty easy no. You should not be concerned because these particles aren't really traveling this whole distance. The wave is traveling. The wave is going across. But the particles, they're just vibrating back and forth, back and forth, back and forth. Remember, it's that chain reaction. That's how the sound is traveling. Okay, so we don't have to worry about this. You're not hearing this in the news that we need to keep this sonic distancing, right? It's okay to listen to someone talking because it's not like their saliva is going from their vocal cords into their ears, unless they're like spitting at you. And if that's the case, you got a whole other set of problems. And you know I'm here for you. Okay? So those were the homework problems. Again, email me any questions. Hopefully you skipped around just to whichever ones you needed. Hopefully this was helpful. Thanks for watching.